As a network administrator, keeping your network running smoothly is one of your highest priorities. Let's go over how you can become familiar with your network segments and with some high availability routing protocols you can use to your advantage when links go down. First, let's discuss subinterfaces and the role they play in maintaining connectivity. Physical interfaces can be divided into multiple virtual interfaces known as subinterfaces. These are used to route traffic between multiple networks. Before we get into the details of how they work, we need to do a quick review of how a VLAN works. First, remember that the whole purpose of using VLANs is to separate traffic. In this example, PC1 and PC3 are able to communicate with each other because they're both on VLAN 10. And likewise, PC2 and PC4 can communicate with each other as well. But PC1 and PC3 can't communicate with PC2 or PC4 because they're on separate VLANs. Obviously, there may be times when you want to route traffic between VLANs and you need a router to do that. But what if your router only has one interface card? That's where subinterfaces come in. For example, if your router only has one physical interface, but you need to connect to two different VLANs, you can't create two subinterfaces for that card, one for each VLAN. Each subinterface can then be assigned its own IP network address and other related IP information. With this example, you now essentially have three interfaces, the physical interface and the two subinterfaces. In many routers, such as a Cisco router, the parent physical interface sends and receives data for the subinterfaces. But how does the router know which network or VLAN to send the data it receives? This is done with tagging, or as Cisco calls it, trunking. The most common protocol used for tagging is 802.1q, which is often shortened to just dot1q. The purpose of tagging is to identify the VLAN the data is either coming from or going to. It inserts a tag into the Ethernet frame that contains the VLAN ID. Let's see how this works. As you saw earlier in our scenario, we have a switch configured with two VLANs, VLANs 10 and 20. Since our switch is a layer 2 device or data link layer device, it can't do any routing. We need to add a router to allow packets to be sent between each VLAN. A router is a layer 3 or network layer device. The problem we have in this scenario is that this router only has one interface. So to provide routing to our two different VLANs, we'd need to create two subinterfaces, one for each subnet. Remember that each subinterface has its own IP address assigned to it, matching the corresponding VLAN network. Since these IP addresses don't correspond to an actual physical network interface, they're referred to as virtual IP addresses, or VIPs. We'll discuss those in more detail later. Also know that dot1q protocol has been enabled on this router and switch ports to allow tagging. Although we technically only have one cable for these subinterfaces, it's now as if we had two, one for VLAN 10 and one for VLAN 20. To see how this all works, let's look at a simplified example. Suppose that PC1 needs to send data to PC2. Since our PCs don't know anything about tagging or routing, the frames they send are just normal Ethernet frames. When the frame reaches the switch uses dot1q protocol to insert the tag, which among other things contains the VLAN ID, indicating where the frame came from. The frame is then sent to the router. The router looks at the destination address and sees that the frame is intended for VLAN 2. So it changes the VLAN ID to 20 and sends it back to the switch over the same cable. Remember, we really only have one cable with two subinterfaces. The switch now says, oh, this is for VLAN 20. I know which port that is. It removes a tag since the PC won't know what that is and sends the frame to PC2. Now let's switch gears a bit and look a little closer at virtual IP addresses. First, it's important to know that VIPs don't have to be connected to a single device like we saw in our earlier example. This means that multiple devices can share them. In most cases, though, only one virtual IP address is active at any given time. VIPs are usually seen with one-to-many network address translation or one-to-many NAT. This provides load balancing, enables a router to communicate when data is sent from a private network host, protects the source IP addresses on online private networks, and helps with IPv4 address exhaustion since it allows whole networks to access the internet through one public IP address. Because VIPs aren't connected to a single device, they also provide unrestricted mobility. Additionally, they help us provide fault tolerance through redundancy in case of failover on a single machine. Let's look at one example of how we can use virtual IP addresses to provide router availability. Carefully examine this configuration and determine where the possible single points of failure are. If you look closely, you see there are redundant connections between the switches on both LANs. So as long as the switch the computers are connected to doesn't fail, we'll have multiple ways to get to the router. But notice there's only one link between each LAN and its associated default gateway router. Also notice that there's only one link between the routers. If any of these three network links goes down, or if one of these routers goes down, all outside communication for each subnet is cut off. So in this configuration, there are several single points of failure. Now look at this configuration. There are redundant default gateways for each segment. We also have redundant links to the default gateways on each side as well. There are also redundant links between routers. We have a link here, and we have a link here. In this configuration, routers on the same network can compensate for each other if one of them goes down. This creates a problem though, because each computer can only be configured with one IP address for its default gateway. If one of these routers failed, each host and its subnet would need to be manually reconfigured to a new default gateway router address. And that process would be a very time-consuming headache. To get around this problem, we use dynamic routing protocols. For example, First Hop Redundancy Protocol, also known as FHRP, is a family of several protocols, including the Hot Standby Router Protocol, or HSRP. When you enable HSRP, it automates the process of rerouting to a new default gateway. This creates redundancy. You do this by configuring redundant gateway routers on the same subnet to share a virtual IP address and a virtual MAC address. The virtual IP address is the key to how this protocol works. With a VIP, HSRP can dynamically determine which routers the traffic should go to. For example, if one gateway goes down, a redundant router that shares the same virtual IP address can take over for this failed device. Since both routers share the same virtual IP address, the network hosts can't even tell a router went down. Instead, their packets continue to be sent to the same default gateway IP address, and a new router takes over without manual configuration and virtually no downtime. This process works because the routers are exchanging heartbeat messages every few seconds, asking if the other is up and running. This allows the routers to negotiate with each other and agree on what each router will do at any point in time. For example, if one of these routers fails, the other routers use these messages to determine which router will take over the failed one. The newest version of FHRP protocols is called Gateway Load Balancing Protocol, or GLBP. It balances the load between multiple redundant default gateways using an active-active model. This means all the routers actively forward traffic for a subnet. We call them forwarders. GLBP, like HSRP, uses a shared virtual IP address. In fact, all the network hosts use virtual IP addresses as their default gateway router address. But unlike HSRP that uses a shared virtual MAC address, GLBP instead has each router assigned its own unique MAC address. To manage the load between redundant routers, GLBP designates one of the routers as the active virtual gateway, or AVG. The AVG responds to all ARP requests sent to its shared VIP. But the AVG responds to the first ARP request by sending a virtual MAC address from one router and then responds to the next ARP request with the virtual MAC address being used on a different router. This continues through each active router on the subnet in a round-robin style, and in this way it balances the traffic load. Since the different MAC addresses are distributed equally among the network hosts, some hosts send frames to the virtual MAC address on one of the redundant routers, while other hosts send frames to the virtual MAC addresses on the other routers. Now that the load is balanced between the redundant gateway routers, single points of failure are eliminated. It's important to note that if an ARP request arrives at an active router that's not the AVG, that router ignores the request. Only the AVG responds to ARP requests for the shared virtual IP addresses. Each of these redundant routers acts as a forwarder for its own MAC address. Each one listens for GLBP messages to make sure that the other routers are still working. If a router fails, the ones that are still up assume the failed router's virtual MAC address and continue forwarding traffic. In this way, GLBP provides both load balancing and failover. That's it for this lesson. In this lesson, we discussed how physical interfaces can be divided into numerous virtual subinterfaces and that these subinterfaces can be assigned layer 3 parameters like dynamic routing protocols and virtual IP addresses. Then we talked about how virtual IP addresses work and looked at how they're used in dynamic routing protocols. We specifically looked at the redundancy protocols like HSRP and GLBP. We also walked through how FHRPs eliminate single points of failure for default gateways on our LAN segments. And finally, we looked at how GLBP not only provides high availability through redundancy, but also provides load balancing for the subnet.